Where's the here? Hello. Welcome. Yes, ma'am.
It's on Thursday, right?
What?
When's quiz Thursday?
Yeah.
Why did you play it off like that? You're like, oh my bad.
All right. If you are an underclassman, scan it with your phone and fill out the question. Meaning, if you what?
Are there any other classes?
Any other classes of calc? AB or BC. There's 5 other AB classes and 2 BC classes.
Wait, are we supposed to do that?
If you are not a senior,
Oh, wait, junior?
yeah. If you're gonna be here next year, fill it out. If you're not gonna be here, don't fill it out. What? Yeah.
Is it like the official?
So I have to go put a recommendation into Phoenix this year. I get to go say like what I think you should do. But really at this point in your math career, it's mostly a choice. So I kind of just want to know what you're thinking. And then we get to do like one of my favorite lessons of the entire year. It's gonna make so much sense. All right. So any underclassmen, if you could just scan out your phone. I got my first form. Yeah. All right. I can't think of this on my phone. Y'all, I left my phone. All right. 1, 2, 3. Well, here. We're done. All right. How's everyone doing today? Decent? My dog is traumatized from doggy daycare yesterday. I don't know what happened to him, but now he refuses to go up and down the stairs. All right. So some updates while my underclassmen fill out this form. Again, the reason I'm having you fill out this form, if you are an underclassman, this year teachers will be going in and putting in some sort of like indication of what class I think you should take next year. Really at this point in your math career, your classes are pretty much a choice to you because you're choosing between different types of mathematics at this point. Again, your kind of 2 major options are going to be BC or AP Stats. Those are 2 vastly different classes for vastly different purposes. If you've been enjoying this year, you're thinking about engineering or pre-med or something else that's going to need Calc 2, you may want to consider BC Calculus. You know how the class runs because I am the teacher unless I perish. Yeah. Whoever feels like taking it up. Who's the stats teacher? Miss Royce. She's been doing it for a while. She's had pretty good success. It is a different type of class. So you'll be doing a lot more writing than you think you would be. But her class, everyone's really successful in it. It's a super helpful class as far as like any other major. So if you're considering psychology, you'll need stats. Biology, you'll need stats. Pretty much everything, you'll need stats. So those are kind of 2 good options. There's some other options listed there. If you're interested in any of them, they all count as math credits, but there we go. All right, all my underclassmen, did you fill out the form? Yeah. Cool. We are doing section 6.1. It is one of my favorite sections to teach because you guys are going to think it's easy. And yeah.
Why didn't you like start a new
to give your brain a little time to mellow on the last section we did.
Mrs. Hefty,
Yes.
can we please have Quinn Griffin to the main office?
Sure.
Thank you.
You in trouble? All right. We also get to do one of my favorite number talks. So remember how we spent kind of this entire semester, year, whatever, talking about slope? We have a new question we're trying to solve. because we're not doing derivatives anymore. Hold. What do you think I could ask you about this picture? Area. That's the new problem. So before I teach you anything, we're just going to do a number talk. So I'm going to give you this picture. You can draw as much as you want on it. You can talk to each other. You can choose to not talk to each other. I know what the answer is. I want you to tell me what's the area of this shape. Closest, I have some extra candy from yesterday. Closest can have a piece of my candy. Ready?
Is it a whole number?
No.
It's a fraction.
Uh,
Or is that
yeah, I have it as a decimal. I think it is rational though.
If we get it right,
You
like,
won't?
but if we do, then can we like not do the lesson?
No. No, because Riemann sums are important and you're gonna find them easy and they're a good way to get 3 points with it.
I have a guess already.
Did you guess already?
Yes.
I have.
That's what
Yes.
Actually, I don't think it is a rational number. I think it's just a decimal.
Russia, they're like tag team training on Wednesday.
I think you know that. All right, so I want you guys, as you're thinking about this, I also want you to think about your method. Some of the ways you're going to be counting are going to be useful in talking about what we're learning today. So I'm going to give you a little bit of time to think about this. Let's try 4 minutes because I really do want you to take a hot second to think about this. So you're trying to find, what do you think the area is? It is a decimal, so probably no one's going to get it on the nose, but we'll see how close we can get. And then I kind of want you to think about, what are you counting? How are you counting? What kinds of shapes are you using? We'll take 4 minutes and then we'll get some guesses going. And I'm going. I'll take 10 minutes later. Yeah, what do we have up for that? I'm not even gonna wear my ring top,
Why not?
so I want to keep it.
I do want to get.
I have a 50 top,
Oh, no, response.
2 refused cards, 1 pink starburst, and 1 pink.
I got no ring toss. No.
No, the ring top's not.
It is less than.
Less than 80. Wow.
Congrats. Wait, what is it? What are the units?
Something squared.
This. Is it not? Less?
No.
Right.
If I don't give it to you, then you don't have to give it back. All right, you still have about 2 minutes to craft your guess. See if you can get closer. Is it supposed to get warmer anytime soon? I'm tired of it being cold. Did I give you guys too much time? No, what? Okay, hold. Satya, what'd you say? 41.3. That's exactly what you wrote down? All right, then I'm wondering if you guys counted the same way. How did you guys count? Okay, when you say the boxes, what do you mean? Okay, so you were like 1, 2, 3, 4. Did anyone else count the boxes?
Yes.
How many total boxes were there? 32 full boxes.
But, my thing is
42.45. Interesting, very accurate. So if you're saying there's 32 full boxes, how are you guys getting the rest of that stuff? What else did you count? Just estimated? That's not very specific. Herbie? Johnny, what did you think? 40.8. Herbie, did you have a guess? 46.3. Chris, what do you think? 39.5? Or did you want a mixed number? Evan? 38. Onyx? 42.9. All right, Leisha? 40.1. Sadie? 40. All right. So after you accounted all those boxes, can you guys tell me a little bit more? How are you finding like this piece, like some of these curvy pieces? Like, what are you doing? I can still take some guesses, Xander.
Yeah, I tried to like match ones that wouldn't make like about the same.
Oh, okay,
I would
okay.
say if it was less than or greater than.
Oh, okay, okay. So, oh, you're saying like this in here should make like one? Okay, so you use some triangles maybe too. Xander, did you have a guess?
Yeah,
43.3. All right. Anyone else want to guess a number at this point? So why you guys are all saying that you use like the boxes, so you use like squares and rectangles and then maybe some triangles. Why did none of you like, I don't know, draw like a circle or an ellipse like up here? What do you mean too complicated? You didn't want to do that math? Okay. Derek said, I don't know the area of the ellipse. So the area of a square or a rectangle is really easy, right? Area of a triangle, a little bit harder, but still not too bad. So there is something to be said for using rectangles and squares, and we're going to talk about that a lot today. Any other things you want to add about how you found this? Yeah, Herbie. Explain. Ooh. Okay. Okay, so you're actually like maybe 5 sections ahead of me. So keep in mind, Hurry's talking about something that we're going to talk about a lot later called average value. That's kind of on average how tall the function is. So if you imagine this like an aquarium where I just like jostled it around and the water's all crazy, if this settled to one height, that would be what average value is called. We'll find a way to find that later. But we need a lot more math before we do that. All right, should we figure out how what the answer is? All right. Let's see if I have it somewhere. Where is my Desmos graph? All right, not this one. This guy. Open. All right, 43.923. I think someone had 43.9, didn't you? 42.9. So 43.923. All right. Still, you guys, very, very close in your guesses, which is pretty cool. So what we're going to talk about today is different ways to approximate, but I want you guys to preserve the idea of rectangles. Rectangles are a really great way to approximate, whether I make them big rectangles or small little rectangles. Rectangles are a great way because their area formula is really easy. So I'm going to hand out notes in a second. We're going to kind of do a bunch of different things with these rectangles. One, we're going to get some language to talk about them. So how do we talk about different types of rectangles that I've drawn? Then we're going to work actually some AP style questions because when we do these with tables, they're actually so much easier. So we're going to hit AP style questions really quickly. And then we'll do kind of a generic one that would be like in a textbook, the first problem you would see, but they're actually the hardest because we got to make all the stuff ourselves. So, we ready? Did I show you a picture of Riemann, the guy with the crooked glasses last time? All right, so if you're wondering who thought of this, his name is Bernard Riemann. He has some crooked glasses. Pretty darn famous mathematician. He was from Germany. He has a lot of contributions to math in general, and his name is Riemann. A bunch of people say Riemann, but that freaks me out. Whatever you like, he's German and dead, so he won't really. In contrast, I'm probably some sort of person since my name is Boston.
That sounds
It does, doesn't it? All right. So we'll do some of these questions, and then we'll probably take a break after a couple of the table ones. I want to get some vocab out of the way first, though, because there's some specific vocab we can use to talk about these rectangles. So, are you already laughing at one of the words? No? Okay, cool. Every year, there's one boy in the back of the classroom who laughs at this word. And it's a struggle. Who would do that? All right, so let's talk about Riemann sums. Now, we're going to be working with kind of a simplified version of Riemann sums where there are a finite amount of rectangles and usually not very many. The reason we're going to be using rectangles, rectangles have a really easy area formula. How do you find the area of a rectangle? Length times width, base times height, whatever you want to think of. I'm going to use the words base and height just because it's going to make a little bit more sense. You're noticing probably in these pictures that our rectangles are usually pretty skinny but pretty tall. That's going to be kind of a theme here. So we're going to have a base and a height. One other cool consequence of these skinny tall rectangles is we can get the area in terms of x and our function y. So here's a kind of formula-ish thing. Oh yes, enjoy our new pencil sharpener. It has a handle that works now. Thanks, Bob. All right. The area is going to be what I'm going to call a delta x times an f of x. When we think of this delta x, we're going to think of a little change in distance along the x-axis. So that's very similar to our base, the kind of skinny bottom of that guy on the x-axis. And this is going to be like our height. So that's going to be our function value. So notice we could grab that by choosing whatever part of our rectangle is kind of on the function. So we're going to be concerned with a base and a height. Now, there's some different ways I can talk about these endpoints. I'm going to mention kind of the first set of words, but we're really not going to use them that much. So our goal eventually will be to find actual area under the curve. That's not what a Riemann sum does. The Riemann sum helps us to approximate. So today, we're not going to actually find area. That'll be with calculus. Today, we're going to use some rectangles to approximate. One way I can describe those rectangles is by describing inscribed rectangles or circumscribed rectangles. Inscribed, notice all of them are kind of inside my curve, meaning between my curve and the x-axis. Circumscribed, they're kind of over top of that curve. This will give me an underestimate of my area. And this will give me an overestimate of my area. Exactly. So we're just, you could, to get a better estimate, because our graph's curvy, it wouldn't give us an exact answer, but it could give us a good idea. Now, these end up being really hard to actually do because we want a consistent part of our rectangle to be touching the curve. So notice here, this is like the left endpoint, somewhere in the middle, left endpoint, maybe the left or the right, somewhere in the middle. That's actually really, really hard to evaluate what part of the rectangle or what x value I should plug in to find that height. So we're really going to be focusing on these green ones down here. So in our questions, Riemann sums are really, really great because they're super straightforward and they're usually going to tell you exactly what endpoint they want to be on the curve. Notice here when I say left endpoints, the top left corner of each of these rectangles is on our function. So that top left corner there. That's going to give me a consistent way to find that function value to plug in. It'll make sense once we go and start doing some questions, but the left endpoint just means the top left corner of the rectangle is going to be there. All right, right endpoint, exactly what you would think. The top right corner of each rectangle is on the curve. Again, giving me a very consistent way to figure out what x value to plug in. Where do you think the midpoint is? Wow, brilliant. Right in the middle here. Which one of these types, left endpoints, right endpoints, or midpoints, do you think usually gives me the most accurate? Yeah, midpoint usually does. Now I could have a crazy looking function where that isn't the case, but usually the middle one gives me the most information, which probably means that the middle one's the hardest one to do because usually the better the approximation, the more difficult. All right, the last thing we're going to talk about before we actually go and start doing some questions is how we can tell if something is an overestimate or an underestimate. And there's actually a really good pattern for these if we have a strictly increasing or strictly decreasing function. So what I would like, I want you to kind of look at the pictures of the green ones or the ones on your paper that aren't green but correspond to the green ones on my paper. And look at these guys down here. I want you to try to decide, are the left and the right for each of these an overestimate or an underestimate all the time? So try to look and see if you can write, like, can you write over here and under here? Or is it the other way around? Are they both overestimates? Are they both underestimates? I'm going to give you a couple of minutes to think about it and try to see if you can tell whether on an increasing or a decreasing function, the left or right endpoints would be over or underestimates. Feel free to drop on those pictures. I'll give you a couple minutes to ponder. What? E to the x. Or e to the negative x. It's my favorite function. Does anyone think they know already? You guys are thinking faster. Anyone want to make a claim about this first graph? I kind of drew some of them in. Left is under. Ooh, that guy's thick. All right. Left guy is under and right is over. Do you guys agree? All right. Could anyone give me, they don't have to be great words, but some words as to why that's the case? Okay. So why does that make it an under approximation? Okay, so when we draw this picture, I kind of like what Johnny's saying. You can kind of see that if we're using the left endpoint, we're using the lower of the two options. So we're kind of missing out on some stuff as we go. It's easier to see towards the steeper end. And on the right-hand side, we're kind of gaining some extra stuff over there. Now, I know I'm drawing rectangles that are one wide. I definitely don't have to. I could draw them a lot bigger, and that exaggerates this idea. If I use the left endpoints over here, is it going to change or is it going to stay the same? All right. I heard someone whisper it's going to change. So this should be an over now. Notice we're using the higher, so we got all this extra stuff right here. That's not the area under the curve. And then if we're using the right, we're kind of under approximating here. Again, you can draw any sort of rectangles you want to look at that. But that will be relatively consistent. Now, midpoint we won't talk about as much with over and under approximations because that actually has to do with the concavity of the graph. So it's a little bit more difficult to figure out. So we're just going to deal with increasing, decreasing, lefts, and rights. So you may be like, all right, you told me a bunch of words. Let's actually do a problem. Would love to. Let me show you a picture before we do get started. So Riemann actually, we're going to do ones where there's like 5 rectangles, 6 rectangles. Riemann actually was like, well, what if there's infinitely many rectangles? And you can set up one using some summation notation where there's lots of rectangles. And you can kind of notice that the more rectangles that I do, the closer to the area this looks like. So here's like 1 rectangle, not a great approximation. But as I play, notice the more rectangles I use, the better this looks like, the closer the approximation. So what Riemann did is he said, well, what if I can do infinitely many? And he also generalized it. So unlike this picture, the rectangles could be different sizes. So you could do one that's like real fat, real skinny. They didn't have to be kind of equidistant along the x-axis. So this can get really good. And if you can push that number of rectangles to infinity, you actually get the area under the curve. And it doesn't matter if you're doing lefts or rights. This one happens to be a right Riemann sum because that right endpoint is on the graph. How beautiful. Now we're going to do like probably 6 rectangles at max because it gets a little bit boring after a while. So we're going to start when we are given a table. These are going to be very AP in style. So you're going to notice there's kind of a paragraph of text at the beginning of a lot of the questions we're doing. But these actually end up being easier questions because once I have a table, the question's pretty darn easy to do. Herbie.
Keep adding rectangles for it. Number of rectangles for like it'll be the correct.
If you get infinity. So I could do a limit and push that number towards infinity, or an equivalent limit could be to take the x distance on the bottom and push that to 0. So they're like infinitely thin. If you could do that, yes, you absolutely could get the right thing. And we can look at that next class. I might add it back into our notes of how to set those up. They tend to be a little bit weird because you have to set up a formula for each rectangle that's dependent on how many rectangles there are. So it gets a little bit finicky. But if I could set up that summation, then yes, I could actually get it, which is pretty cool. So let's go ahead and we're going to do some smaller ones. Now I'm going to at first draw a picture of these points to get an idea of what we're doing. Eventually, the pictures that I'm going to be drawing off to the left-hand side of the screen aren't necessarily ones that you would have to do. Love this color. All right, so notice here we do have quite the block of text here. But we are looking for very specific words. One thing a lot of my students like about Riemann sums is they're not really secretive about what you're supposed to be doing. They're going to come right out and say exactly what they want you to do. Thanks, Bill. So we've got a function f. It's continuous from 2 to 14. That's the stuff we can see on the table. We've got very selected values. It tells me what sub-intervals to use. So that's kind of how we're going to break up our interval into the rectangles. We want an approximation found by using a right Riemann sum. So this right, left, or midpoint is always going to be given to us. Usually they'll use the word Riemann here, but we're kind of going on the idea of approximation for the area. So we've got some sub-intervals. Now, when you see me do this on my normal paper, you'll usually see me block out my rectangles like this. That's going to correspond to how I'm thinking about this on the graph. So for the first couple of questions that we do today, I'm going to actually draw a graph to the side. This can really help you as you start visualizing what we're actually doing. So I'm going to draw a quick sketch of just these 1, 2, 3, 4 points on my graph. I don't know what the rest of f of x looks like, but it can give me a good idea. When I say sketch, it's not going to be perfect. It'll just be okay. So let's see, I go up to 34. So maybe count by tens and I'll go up to 40. And I'm just going to count, and every time I hit one of these numbers in the x's, I'm going to label it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, I'm going to try to plot these 4 points on my graph. Doesn't have to be perfect. So 2, 12, 5, 28, 10, 34, and 14, 30. So we could imagine here that our f of x might be some sort of parabola. It's kind of going up and coming back down. I don't really know what it is. I am just going to try to find an approximation to the area under this curve. So one thing I like to do on this picture is kind of drop a vertical down to the places on my x-axis. These are the possible heights of my rectangle. My possible widths are kind of down here. So my job is going to be to do a kind of base times height, a length times width for 3 of these rectangles, but I have to figure out which ones the heights are. So for this first rectangle right here, based on the words in the question, am I going to be using the function height at 2 or the function height at 5 to make that rectangle? 5. It says the right Riemann sum. So I'm going to pull this guy over and drop him down so I create a whole rectangle there. Let's go ahead and write the area of that rectangle real quick. So I want to know how long is that rectangle along the x-axis. 3. It's from 2 to 5. If you wanted to label in your table, wow, that rhymed. You're talking about doing 5 minus 2, or you're going 3. So this is 3 times how tall is that rectangle? 28. Notice I have 2 y values here, and I chose the right-hand one. Not very surprising. Is that what 3 times 28 is? 60, 84. All right, let's try the next rectangle. All right, how long is that rectangle along the x-axis? 5. You can label it up here if you would like, but you're going 5. And how tall is that rectangle going to be? 34. We're using the right-hand side on here. If you're visualizing on your graph, you've got 34 tall. No. So I'll show you what I would actually draw when I get here. I think it gives a great visual at the beginning, though. So that's why I'm drawing it here right now. All right. The last one, how long is he along the x-axis? 4. All right. How tall is he going to be? 30. Again, we're using that right-hand value for that guy. So I'm going to have 4 times 30. All right. I believe this one was a calculator question, but you can try to do it in your head if you would like to. Herbie's claiming 374. Would anyone else like to support? Cool. So Johnny's asking a really good question of what are you going to actually write down if you're doing this work? So this is actually equal. If you wanted to write the approximate, you're right. We're going to eventually use that notation. You could say the area is approximately that, but those three numbers added together are exactly equal to 374. So that and equal sign is okay. We will get some notation for this. Evaluate it and just say equals 374. Yeah, we're going to get some notation for what this is, just like we have our derivative notation. So that would be what we could set equal. I'm going to save that notation for a couple classes from now. So we got some learning to do before that. So the question becomes, how much work do I need to see when you're actually doing this question? Theoretically, the stuff that's just in the colorful notation there and equals 374 is fine. Usually I'll do kind of this notation on my table, but I won't usually draw the picture. That being said, the first couple of times you try this, the picture really does help justify why we're doing some things. I get a lot of students who want to like add these guys together because you're adding some other stuff. So just figure out what works the best for you. If you're getting confused though, drawing a picture and actually seeing the rectangles can be really helpful. All right, shall we try one more together? And this was a real AP test question. So if you could do that, there you go. I like these questions a lot. All right. So here's another one. This one was actually from a free response question. It's part of one of my favorite types of free response questions called rate in, rate out questions. Yeah. They literally told us in the question. They will. Yep. Yep. So good question from Matt. What if they don't tell me? They will tell you what type of Riemann sum to use. The only way I could get really complicated on that is if I had a strictly increasing or decreasing function. I could tell you to circumscribe or inscribe, and then you'd have to draw a picture. But that's very rare. They're usually going to tell you exactly what they want. So let's kind of finish out this page, and then we'll take a break. We'll take a break really quick. So looking at this guy, this was an actual free response question off the AP test. Remember, you have those 45 multiple choice and then the 6 brain-killing free responses at the end. This one was part of a rate in, rate out question, which is really cool. They're one of my favorite types of free responses. We'll definitely do one as we practice for the AP test, and within this unit, we'll talk about them as well. But we've got some units on here, so we can start to figure out what this integral or Riemann something is doing. Sorry, I'm going to start using some words that we haven't talked about yet because I teach BC as well. So let's kind of read this paragraph, see if we think any important things are coming up. So we've got water in a tank, and we've got the rate at which water is being removed from this tank, and that's our R of T. So notice that does have rate units. It's liters per hour. We know that this function is differentiable and decreasing. Now that word for me feels important, that decreasing. We'll kind of highlight that and come back to it. We've got selected values of R of T in the table, so we only have specific things in this table. And then we've got this kind of weird piece of information. At time 0, there are 50,000 liters of water in the tank. I don't know what that is yet, but it feels important. Now, again, notice, kind of like Matt was asking about before, the Riemann sum part of this question is going to be very specific. So use a left Riemann sum with the 4 subintervals in the table. So they're telling you exactly how many rectangles. That's kind of your subintervals thing. This corresponds to how many rectangles you're going to have. And it tells me which function value to use. And we're going to estimate the total amount of water removed during the 8 hours. So I'm going to figure out at the end of this how those units are working out. Let's, for the sake of just doing our second example ever, draw a quick picture of this to, again, justify why we're doing the things that we're doing. So again, I'm going to kind of creepily do the side. I'm going to count by, let's see, I'm going up to almost 15. I'll count by 500, that's fine. So here I'm just doing a quick sketch, trying to get an idea of kind of what this looked like. Doesn't have to be perfect. Again, I'm going to label everywhere I have one of these numbers. Your sketch could be more detailed, less detailed than mine. Eventually, you probably won't need to use it, but for right now, it gives us a good idea. So there's 0, 13, 40. 1, 1190, 3, 950, 6, 740, and 8, 700. Again, I'm going to drop those verticals as kind of the potential heights of my rectangle. All right, we are guaranteed that this function is decreasing, so it's not doing anything crazy in between. But we don't know exactly what it looks like, so I'm just going to leave that off. All right, let's get some rectangles going. So the first rectangle we're talking going from 0 to 1. So I know that this is the base of this guy. Which one of these heights, the height at 0 or the height at 1, so 1340 or 1190, which one is going to function as the height of this first rectangle? All right, the 0, the 1340, because that guy is to the left. So I've got that first rectangle. Let's write the area of that rectangle. You guys said he's 1340 tall. How long is he along the x-axis? 1. You could do 1 minus 0 here, label it with a 1 there, whatever you want. It's another 1 after that? All right, how could I figure it out? No? Or count, that's fair. So if you have a picture, you're kind of reducing this to counting, which is nice. We could go from 1 to 3. We have to add 2. How tall is that guy going to be? Yep, the 1190. That is the left-hand number on my guy here. So we've got 2 times 1190. All right. What? So notice here, if I have this next rectangle, my stupid pen keeps trying to make a pretty picture. So I have 2 possible heights for this rectangle, either the one that's on the left or the one that's on the right. Since this guy told me left, I want to use this height right here at 3 to complete that rectangle. If it were right, I would want to use this one right here. So it's whichever end point would be on your curve. So you've got your left and your right. All right, what is my area formula for the next one going to look like? Plus what times what? 3. Beautiful. All right, so notice we're doing the distance in between these two times the number that is to the left this time. All right, without even drawing, does anyone know what the last one's going to look like? Perfect. So you might already, even though we're only on our second question ever, you might already be thinking, I probably don't need this graph as I go. You don't have to draw this graph by any means. I just want you to know when I'm labeling this guy up here, what I'm looking at. I'm looking at the distance between the x's, and then I'm choosing one of the y values based on the kind of word in my question. So oftentimes you'll see kind of that notation from me on the table, but I wanted to connect it back to the graph to get a visual. Also notice, which is the one y value that we didn't use in the table? The last one, would you agree that that's the rightmost y value? Maybe the left one. Wow. All right, can you guys find me a number for this? If you need a calculator, they're over there. And then see if you know what units you could put on it, because this question actually does have units. Anyone got a number? $8,050. Does anyone have some units? All right, they are liters. Now, did you do that by reading the question and it said total amount of water, or did you do it by looking at the units that you used in the question?
Liters per hour at the top.
Okay, So let's look at these units right here to justify, because I agree, total amount of water should be in liters. Let's look at the two things that we were multiplying together. The RFT values, so the big ones, the 13, 40, 11, 90, 950, these were liters per hour. These units, the 1, the 2, the 3, the 2, those were measured in hours, yes? So we have hours times liters per hour. Those hours are going to cancel. I should end up with liters. So the units do make sense with the math we're doing as well. All right. Further question. Is this an overestimate or an underestimate? Wow, you guys all said that really quickly. How did you know? How do you know it goes above the graph? Okay, so you're saying that the function has to be doing this. All right, it looks like it. How do I know the function's not doing like this? What word? There's one word. We have a decreasing function. So we're going to say because r of t, our function, is decreasing. You can also mention that we used a left Riemann sum, but they wrote the question. They know that the Riemann sum was a left Riemann sum. But the fact that that function is decreasing is what tells me that it's an overestimate. All right, the last thing we're going to do before our break is just take a peek at what we can do with something like this. So we're going to take this number and we're going to incorporate it into the rest of the question. I want to know what the total amount of water left in the tank after 8 hours was. So notice that the 8050 is the total amount of water that we removed. How do you think we could find the total amount of water left?
Difference?
All right, we could subtract 8050 from something. What are we going to subtract it from? 50,000. This number up here, there was the number that was in the tank at the beginning. So we can get 41,950 liters of water. We're going to extend this type of question where we might also get information about a rate in. If we knew how much water got added in, we could add that to what we're doing now. A very popular style of free response that you're probably going to see, I was about to say on the SOL, on the AP exam, but one that's really cool and really thinky, where you can kind of just think it out. All right, we like this so far? Not too bad? Just shut up? Okay, cool. Let's take a break. Take 4. When we come back, midpoint, and what if we don't get a table? Then we'll be done. I don't know what to do on my break since I forgot my phone at home. It's a struggle. You guys are allowed to talk, I'm sure, if you want to. Or we can just keep it real quiet. Sorry, fine. All right, you guys ready for the spiciest of the three options? A midpoint, Riemann sum. You guys sound really excited. Please contain your excitement. All right, so we're gonna do another one. Again, this is straight off of the AP test. Another one where you're given a rate in a table. If you see a question like this, get excited. Riemann sums are coming your way. So we've got a coffee maker. It's filling into a large cup with coffee. We've got the rate at which the coffee is going into that cup between 0 and 6. We've got selected values in the table. Sweet. Now, let's look for some important words. Not timers. We want a midpoint Riemann sum with 3 subintervals. What does the word subintervals mean to us again? Rectangles. That's how many base times heights we're going to be looking at. These are going to be of equal length. Now that's interesting. Some of these were not of equal length. Actually, I don't know if we've done one with equal length yet. When I say equal length, I mean like that 1, 2, 3, 2 is going to be a specific number the entire time. All right. We want to approximate the amount of coffee that fills the cup. Huzzah. All right. So 3 subintervals. How long is each of the subintervals going to be? 2. Does everyone see how Johnny's getting 2? We're going from 0 all the way to 6. So that distance, 6 minus 0, all over how many subintervals I have. So each one of those is 2. That's a cool way to do it if you can't think of it on your own. But let's draw a quick picture just so we can see what's going on. 4, 5, 6. Let's count by 5. Again, after today, if you don't want to draw this graph, by all means, you don't have to. 1, 5.3, 2, 8.8. Yeah, I think it is 2. Just takes a little bit of time. 1, 2, 3, 4, 5. 13.8. All right. So each of these is actually going to be too long, and there's a reason for that. We're only going to have 3 rectangles. Now I'm drawing mine so super weird. I'm missing a dot. 1, 2, 3, 4, 5, 6. No, I'm not. Oh, I am missing a dot. Where's my last dot? So we want to think we're going from 0 up to 6, and we want to take 3 steps to get there. So if you want, you could take the length of your interval, kind of the end minus the beginning, and divide by the number of rectangles. So that's what I wrote over there, the 6 minus 0 over 3. Or if you think of starting at 0 and counting up to 6 in 3 equal steps, you do 2, 4, 6. All right, let me try to plot these again because I skipped a dot somewhere and I cannot figure out where it is. All right, that's a little bit better. So here's my 2, here's my 4, there's my 6. Now, the reason we're setting this up like this is notice I'm not going to need to use every single kind of height here. So looking at this first one, I'm going from 0 to 2. The second one, I'll be going from 2 to 4. And the last one, I'll be going from 4 to 6. Now, there's a reason they're setting us up with 3 subintervals of equal length instead of 6, and that's because they're using the midpoint formula. So if we look at this on the table, notice we have 3 y values to choose from. Here we have 3 points to choose from. If I'm looking at which y value to choose, which one am I going to choose? The one in the middle. If you want, you can use your hands on your piece of paper to cover up everything but you're looking at. You should be using that 5.3. Now, I wouldn't get a question where I didn't have something in the middle, so I wouldn't be able to do a midpoint if they asked me to use 6 subintervals here because I wouldn't have the middle values. So you'll kind of be skipping those. So that first rectangle is going to be 2 times 5.3. What's my next rectangle going to look like? The area formula, that is. 2 times, yeah, the 11, that one in the middle there. Again, you can draw the graph if you want, or you don't have to. I think it does give a good justification to why things are the way that they are. Because of this word midpoint right here. So we want, if I change this to left, I would use 0. If I change this to right, I would use 8.8. Middle is here. And we'll always, if we're doing this, we'll always have like less subintervals than it looks like on the table so we can have that middle value. All right, what does our last rectangle look like? 2, 13.8, perfect. All right, so notice we again have that middle value. All right, anyone calculate while I was talking? Cool, that's okay, I already have it. This is 60.6 if I did my math right. All right, anyone know what the units are on that? Ounces. 2 ways to think about that. It asks me for an amount of coffee, which can be measured in ounces. Also, we took minutes, were these time intervals, and then these were in ounces per minute. So those minutes will cancel, and I'll just get ounces. So a good idea of what we're going to be doing as we go forward. I kind of told you guys last class that we were going to be reversing everything we did. Think of derivatives. We took derivatives and went from like an amount of coffee to a rate of change. Notice we're kind of doing exactly the opposite here. We're going from a rate of change to an amount of stuff. So you can kind of already see what's going on. Now I'm going to skip this part because I actually would not ask you this question for a midpoint Riemann sum, whether it's an overestimate or an underestimate. Again, that would have to kind of do with the concavity of the graph, and we're not given information about that here. Right or left, we could determine underestimate or overestimate, but you won't be asked that about midpoint. All right, so off of a table, pretty darn easy. What I do want to show you is one where we would have to make the table. So we're going to do a generic function here and kind of make our own table, and this will be the last example we do for today. I just want to show you what the difference is between one where we get some context with a table already given to us and one where we have to make our own. So let's play with the graph of x squared plus 1. We're going to play it between 0 and 1 on our x-axis. Anyone know what the graph of x squared plus 1 looks like? Yeah, I would agree. It's parabola. Let's go with parabola, but yes. Yeah, it's like a U shape. So it goes through the points 0, 1 and 1, 2, because 1 squared plus 1 is 2. So we kind of got this And Sadie's right. If I graph the other side, it would kind of make that U shape right there. All right, so notice here, we do not have a table in this question. Yeah, sure. All right, we don't have a table in this question, and the first step is really going to be to make one. So even though if you kind of looked in a textbook, this would be the first question you would see of just making the table and doing it yourself. I actually think the AP questions are actually a little bit easier because they have the table already made. So we're going to kind of reflect what we were doing up here, and I'm going to try to make a table of x's and f of x's to plug in. Now I want my first value to be 0 and my last value to be 1. How many rectangles do I want? 4. I have 4 subintervals. So I want to count from 0 to 1 in 4 steps. How big is each of my steps? 0.25 or 1/4, right? I'm team fractions, so I'm going to count by fourths. You can count by 0.25s if you want. So I have 1/4, 2/4, which is a half, 3/4, and 1. Now, if this were a more complicated interval, to find what that delta x is, the amount I'm stepping by each time, you can do your end minus your beginning all over your number of rectangles. So this interval is your a to b, so you could do 1 minus 0 all over your number of rectangles, which is 4. Just in case your interval happened to be like 2 to 17 with 53 rectangles. All right, how do you think I'm going to get the f of x values? All right, 0 and 1 are easy. Okay, what about the 1/4? Seventeen sixteenths. That's correct. How did you do that? Perfect. So what Saskia is doing is she's using our function right here, x squared plus 1. She took 1/4 squared, that's a 16th, plus 1, which is 16 16ths. That's 17 16ths. Hopefully that's what she did. Cool. All right. How about 1/2? What do you guys think? Five-fourths works. That's 1/4 from the x squared plus 1, which would be 4/4 in this case. All right, last one. We got 3/4 squared plus 1. What mental gymnastics can we do today? I do agree at 16. How many did you say? I think it's more than that. What is it? 25? Because we have 9 plus 16, so that should be giving me 25. 16. All right, let's go ahead. And this one, if you'll notice, doesn't say left, right, or either. That's because I want to do all of them. In any given question, you would be given all of the directions, so that it would tell you which one. I want to do all of them just to show you how we could do it. All right, do you guys want to try left and right? You guys already know how to do that? No? We should just all do it together? We're tired? All right, left. Let's see if we can do that just by blocking off the table. All right, look at the graph if you want. What is my first rectangle going to look like? For my left Riemann sum, which I'm doing green. How long is it along the x-axis? 1/4. How tall is it? Yeah, you're right. 1. Got to use the left one. What's the next rectangle going to look like? Is it still 1/4 long? All right. How tall is it? Wow. All right. How long's the next one? 1/4. You might be thinking to yourself, why don't you factor out that 1/4? I like to see 4 base times heights, so I'll always keep it unfactored. But if the Riemann sums are the same length along the bottom, you could certainly factor. How tall is that third rectangle? 5/4. How long is the next one? Oh, okay. How tall is it? How long is the next one? Good. That's one reason I like to keep it unfactored is I can see my 4 base times heights, and I'm using these 4 values. What's literally the only thing I have to change to do the right-hand one? There is very little that has to change. What has to change? What I'm changing from left to right. All right, the 1 and the 2. The first rectangle with the 1 is out. The last one with the 2 is in. So I could do 1/4 times 17/16, 1/4 times 5/4, 1/4 times 25/16, 1/4 times 2. I'll be your calculator for a second. I got 1.46875 for this guy. 1.21875. What do you know about the actual area? It should be between those two. Anyone have a guess? You can do it that way. Absolutely. Actually, wait. No, that's something different. That would work if this function were linear. It's not, since it's curvy, the midpoint actually is slightly, in this case, lower than what it would be if I averaged them. You're actually doing what we're going to do next class, which is what if I make a weirder shape. If I wanted to do the midpoint, I actually need some different values because I need the height here, I need the height here, I need the height here, I need the height here. I don't have those because they would be like right here. Think of the questions we just did. Yeah, so I'd have to find those. So let's do that real quick, and then I promise I'll stop talking for today. Exactly. That's perfect. So what we would do here is we would have to, do you agree that they are all still going to be 1/4 long, regardless of where I'm picking the height for this? So I would have 1/4 still. But Matt's right. I would have to plug 1/8 into my function. So directly between 0 and 1/4, think of 1/4 as like 2/8. So directly between 0/8 and 2/8 is 1/8. Yeah. How did I find the values in the f of x part? We took this function right here, which was our f of x, and just plugged the x's in. You could certainly do them in decimals. I just think thinking in fractions is I like. All right, so Herbie's right. We could convert this into like 65/64 if we wanted to. So here I plugged in 0, 1/4, 1/2, 3/4, and 1. We were counting by 1/4 from 0 up to 1. Because we wanted to go from 0 to 1 in 4 steps. And we wanted to go in 4 sub-intervals. All right, let's see if we can remedy some of these questions because I hear some more going. Let's look at our next rectangle. I think it's going to be 1/4 long. They all look like they're going to be 1/4 long. How would I figure out how tall it is? So I'm looking for this height right here. All right, Derek's claiming the x value would be 3/8. Do you guys agree with that? We're going between 1/4, which is 2/8, and 1/2, which is 4/8. I think right between that would be 3/8. Now, 3/8 I can't just plug in. That's an x value. I would need to find the y value here. So again, I could plug it into the function. It's not in our table. If I had been forethinking enough, maybe I would have counted by 1/8 in my table. So I'm looking for the middle between 2/8 and 4/8 because I'm looking for right in between 1/4 and 1/2. So I'm looking for the middle x value there. So the next one, we need directly between 4/8 and 3/4, which is 6/8. What would I be plugging in there? 5/8. Again, I might have made this in my table if I knew I was going to be doing this last one. All right, what do you think the last one's going to look like? 7/8. And again, I'm plugging into the function because that's how we did it in the table. This guy here is 1.328125. Anyone have a guess for exactly what this is? I think I know.
Why do you square it after? Oh, because it's like.
Because I'm plugging into this function. So we did that in the table here with the original values. Here, since I didn't have these middle values in my table, it's like I was finding the x and the f of x all over again. So I'm taking the x's that are the middle guys here, since I didn't have them in my table, and I'm plugging them into the f of x's. So this is like this 1/8. I'm finding how tall it is there. This 3/8, how tall. I took x squared plus 1, still plugged in 1/4. So 1/4 squared is 1/16 out of 1, which is 16/16. All right. Cool. So the vast majority of the time, the way you're going to do these questions is the way we did them at the beginning, where I'm going to give you a table, give you some context, and in the future, this context is going to get more interesting the more that we learn about this unit, because we're going to actually be able to find area under a curve. The actual area for this one? Anyone have a guess? Which one's the closest? The midpoint is definitely the closest. It's a relatively nice number. Can anyone think of a relatively nice number? I think it should be 4/3. So 1.333 repeating. We'll find out how to find that in like 2 to 3 classes. All right. So that's pretty much it for Riemann sums. We are not going to learn anything new next class. Does anyone know why? We have a quiz. Did I say that was going to be a partner quiz?
Yes.
I did?
Yes.
All right. I think you're lying to me, but
I remember.
No, you actually did.
I did?
Yeah.
All right.
You like considering it.
All right. I can't. Oh yeah, I did say that. Sure. I don't know. I'm doing a partner quiz in my BC class as well. So next class we're gonna have a quiz, and that's gonna be on Unit 5. A reminder for that quiz: you have this optional problem set. I would highly recommend trying these problems out. I am not that creative when it comes to Unit 5, so your quiz is probably going to look vastly similar to this problem set, meaning I'm probably just going to change around some functions. I'm probably not going to change a lot of the wording. I may make it a little bit shorter just to get kind of good amount of time for you to do this problem set, kind of do the quiz in class. I imagine it'll take about an hour, so we'll have like the first 20 to 30 minutes of class just to hang out and make sure we have everything done and ready to go. And then you're going to be doing this. I will probably give you guys a short round to the following class just to fix any mistakes. That being said, I have tested on this like little mini unit for years and years now, and I can tell you what's painful. If you don't have these derivative rules memorized, please, please, please don't walk in next class without being able to like directly answer me when I say, what's the derivative of arctangent x? If you don't know that, you're gonna have a bad time. So please, 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 I could make a meme out of it if you would like. Please, please, please have your derivative rules memorized, because it's not gonna be fun, and I'm not going to help you if you don't have them memorized. A lot of this is just very specific facts, but this is about about the difficulty level I'm going for. If you would like to turn in this optional problem set for points, I'll take it by the end of next class, so feel free to turn in whatever you would like. I will grade it, and if it helps your grade, I'll keep it in the grade book, so I'll probably put it in at the beginning since we don't have a lot of grades yet, and then you can kind of fix from there. Absolutely. All right. We have one thing between us and the end of class, and that's a notes check. So we're gonna play with some Riemann sums. I'm gonna say it's gonna be more like these questions where you're already given the table. I do want to put out a warning though. I wanted to give you guys a couple of context here. So while there is one table, you may not use the entire table on the question that you're working on. So for example, this table goes from 0 to 80. But the first question asks you to go from t equals 70 to t equals 10 to t equals 70. So you won't be using the same table, like the same parts of the table for the whole thing. Also, there are 4 versions. It's all the same table, so you can help each other, but don't copy them. We good?
Yeah, great.
Cool.
Stellar.
All right. Yes, I'm picking the partners for next time.
It's a partner quiz?
Yeah, absolutely. So we can have you take it alone for you, so we call it usually a partner, because if anyone else is interested in our class, I can try to meet up, or if you want to get rid of it, I can do kind of a slightly off of it, or like, yeah.
Oh, yeah.
All right, so I need this before you leave. I'm also gonna take a second to hand back some notes check forms that I have. I believe I have all of your Unit 5 ones, so if you wanna do some corrections on those to practice for the test next time. If I remember correctly. 3 questions, I know. I'm a terrible person. It might be because we have left, right, and midpoint. No, the 22nd. No, right? All right, so I'm importing notes check. I'm gonna pass all the numbers back. This will be a great way to study for Unit 5. Like, same table. Yeah. Oh, sorry. I think it's
Hey, trying to guess, like,
I think I left it for I didn't know what the M value was.
what does it say?
Oh, wait, oh, it's medium, yeah.
How does he
Yeah, if you guys have any extra time, because we still do have about 10 minutes, you're more than welcome to work on correcting those. All right, if you're getting less than 3 notes checked back, that probably means I'm missing one from you. They're in that blue binder over there. Or you can just yell at me which one you need. There's one for 5152, one for 52. Oh, okay. Oh, it's the same one.
Oh.
So if I wanna go from 20.